Morning, everyone. Thanks for joining our NMIS Insights webinar this morning on lightweight solutions for a net zero world. If you don't mind just bearing with us just for a moment, just to let people connect. Thank you. Okay, good morning again, and thanks very much to those of you who have just connected to our NMIS Insights webinar on lightweight solutions for a net zero world. NMIS is joined today by Florian from TGM. But for the moment, I'll now hand you over to my colleague at NMIS, Stephanie Craig. Thank you.
Good morning, everyone. Thanks again for joining today. We are delighted to announce TGM as the newest AFRC member, an NMIS member, so welcome aboard. And hopefully you get to know a little bit more about TGM with Florian today. So today's webinar will be presented by Hannah Leslie, who's a Knowledge Exchange Associate within the Design Engineering team, and Florian Whitsold, who is a design engineer from TGM. And Graham McLaughlin will be in the background ready to answer your questions towards the end, and he is a senior design engineer within the NMIS Design Engineering team. So let's get started with some housekeeping. So many of you have already been to some of our webinars, but those of you who haven't, the webinar will be recorded and it will be made available on our YouTube channel towards the end. And your microphone and webcams will be turned off during the session to avoid any background noise. You can type your questions directly into the chat function throughout the webinar. Please use the Q&A function as well, and we will do questions towards the end. If you are on Twitter or you are on LinkedIn, please use the hashtag #NMISinsights for any questions via the Twitter account. And please take some time to complete the survey that will be sent out after the webinar. So for those of you who don't know who the National Manufacturing Institute of Scotland is, we are a group of industry-led manufacturing research development facilities. We're working together to transform the manufacturing landscape within Scotland to become a global leader in advanced manufacturing. We will aim to reduce the barriers to innovation, to enable access to state-of-the-art machining and forming forging facilities, including our digital factory within a research environment where we aim to stimulate the investment and increase manufacturing competitiveness of the companies that we work with. We aim to become a catalyst for job creation and strengthen the Scottish supply chain. And we aim to inspire and attract some new talent for the business requirements. We'll work with manufacturing businesses of all sizes in multiple sectors across Scotland and globally, and providing benefits, hopefully, across the whole Scottish supply chain. Just a little bit about the partnerships that we have. We are operated by the University of Strathclyde, as most of you hopefully know, and we are supported by multiple partners, of which you can see here, so I won't go into too much detail, but collectively we are known as the One Scotland team. So the last slide for me today. So the NMIS group, as I say, for those of you who don't know, are a combination of research facilities. We will have the National Manufacturing Institute, which will be housed at the back end of Glasgow Airport. And within that, we will have the Digital Factory, the Collaboration Hub, and the Manufacturing Skills Academy. Within that, we have two specialist centres. One is the Advanced Forming Research Centre, and the other is the Lightweight Manufacturing Centre. And we're hoping to open the NMIS building in 2022. So without further ado, I'm happy and pleased to introduce Florian Whitsold, who is part of TGM Lightweight Solutions from Germany, and as I said, is the newest member of the AFRC. Welcome, Florian.
Thanks, Deb. So a warm welcome also from my side. And yes, we're also proud to be on board with NMIS. TGM is a company now, I mean, depending on when you say a legal entity starts, maybe 96, maybe 99, who knows exactly, but 20 plus years of experience in consulting vehicles within all industries. We have worked for Airbus, for example, some suppliers also for the rockets Ariane 6, the European rocket program. We work with the big OEMs in the rail industry like Bombardier, Alstom, Stadler, Skoda, and the big automotive ones like BMW, Volkswagen, Lamborghini, and so on. The very heart of our consideration is always we start with which system fulfills the needed functions best, and then we design the mechanical, the structural part around this. Consider at last what material will fulfill these requirements best and generate so a lot of weight savings for all our customers. Hannah, can you go one step? Perfect. We have quite a diverse portfolio of services. I marked those we will touch today. I think we are very much on the left side doing all this. How much will a component weigh? What kind of weight can we still save? And the last and the most important point, and I'm more than happy that we cooperate now and work together with NMIS on this topic, is also to give this some numbers. So everybody probably can come up with an idea how to reduce the weight, but to make this an economical, good design, it is also important to keep an eye on the cost of this. And the battery system we will introduce later in this presentation is now also patented. Thanks, and I hand over back to Hannah.
Brilliant morning, everyone. I'm Hannah Leslie. As Steph says, I work within the NMIS Design Engineering team as a Knowledge Exchange Associate. And I just wanted to start off by kind of starting off this content of this presentation by touching on the importance of lightweighting, why it's continuing to grow in prevalence, you know, why we're talking about it today in this context. So lightweight design and materials have always been an important topic in product design across several industries. I think, you know, historically it comes up again and again in aerospace, aviation, automotive, but also in industries where large rotating parts are key elements of product design. For example, rotor blades, wind turbines, and as I say, in automotive where driving dynamics are a major consideration. Ultimately, why we aim to do lightweight design, it optimizes engine performance and efficiency through weight reduction. So for example, especially in automotive, a 10% reduction in vehicle weight can result in a 6 to 8% fuel economy improvement. Global trends towards carbon reduction and resource efficiency have significantly increased the importance of this topic in this area. Although current CO2 targets for 2025 in Europe can't be achieved just with engine efficiency measures and lightweight design and materials alone, lightweight design will be crucial to enable meeting 2030 electrification targets. This is, as I say, in the case in automotive, but there's also, you know, a focus in rail, marine, aerospace, etc. And the benefit of lightweighting to electric vehicles comes from a reduced battery costs because of less energy requirement, as well as a relationship between driving range and battery capacity. So ultimately, lightweighting might not be the ultimate answer to achieving net zero, but it should be an important shorter term step towards, you know, achieving a solution to what is obviously a hugely complex problem. That being said, there are some significant challenges for companies looking to adopt lightweight design and lightweighting strategies into their product and component development. Lightweighting is not a new concept, and obviously there are a number of limiting challenges in approaching the lightweighting, especially of vehicles. So, for example, although it's understood that lightweighting can be an enabler for net zero solutions, thorough life cycle analysis and assessment is required to fully understand these impacts due to electricity and lightweight material production burdens. Lightweight automotive materials, for example, such as aluminium, carbon fiber, they're very energy intensive to produce, and these are things that do need to be taken into consideration. Other challenges exist in terms of the practical application of lightweight concepts. So what is feasible in a laboratory or in a you know, a single mass optimization study doesn't always necessarily translate to what's practical in production. And proof of concept studies are focused on the goal of mass reduction without always being constrained by real world factors, you know, such as lead time, manufacturing processes, qualification, and the costs of existing manufacturing infrastructure. And so Yeah, implementing new lightweight technology for broad scale mass production does take longer and costs significantly more than what many producers believe is practical. So with these challenges in mind, and obviously a very complex problem, but understanding the importance of lightweight and being able to build a lightweight capability, NMIS and TGM developed a collaboration where we can understand the mass drivers of a geometry, material, method of manufacture, and simultaneously be able to generate the cost drivers and ultimate production costs against a baseline. With this, so within the NMIS side of things, within the design engineering team, we have extensive capabilities in terms of manufacturing process knowledge and design for manufacturing expertise, robust technology and sector agnostic design processes. And crucially for this activity with TGM, we can perform cost modeling and analysis using Seared by Gatherath software, one of our tier 2 members. Where TGM bring their expertise in and where there was real value is in terms of their specialized weight management and analysis methods, effective mass properties and weight optimization. And they have a proven approach for the structured analysis of the variables influencing weight opportunities. So having kind of developed this initial engagement and, we understood that we could put together a repeatable, consistent approach to cost-effective lightweight design and analysis. So as such, we started developing a pilot project to build up and test a collaborative process and to figure out what this process might look like between our two companies. Ultimately, the final goal was to estimate the manufacturing and production costs of an optimized lightweight concept and forecast the preliminary or primary lightweight cost in pounds per kilogram. So we wanted to be able to evaluate the specific potential of a mass optimized concept in order to compare the lightweight cost to a target cost. In practice, this target lightweight cost might not be known, or it may be dictated by the supplier or OEM or through internal benchmarking. Ultimately, we wanted to be able to create a lightweighting approach that was cost effective and flexible enough to work across different sectors, product families and technologies. So in terms of deriving a joint approach to weight and cost optimization, we followed some principles in terms of our existing standard design processes and quality procedures in NMIS, and took into account some of the key information and parameters required for TGM to understand the mass drivers. This begins with defining requirements, constraints, and limitations, and performing baselining in terms of cost and weight. So this can be working with the client through workshopping and other approaches to define the area of focus, establish the weight baseline, and analyze and verify current mass properties, as well as generating baseline cost models for the geometry and manufacturing process. This goes into development of initial sketches, models, or even just understanding of dimensions of potential lightweight concepts that we can then review and take forward for further development and evaluation. So this involves incorporating any design for manufacture input, identifying the most appropriate materials and method of manufacture, defining the cost model of these concepts, and identifying the mass properties and weight reduction potentials. So down on the bottom here, through a series of client reviews and iterations, any feedback can be captured and integrated before preparing final reports and recommendations. And in terms of putting this approach to practice and validating our thoughts, I'll hand over to Florian, who can demonstrate the outputs of our successful initial pilot project together using this approach. Thanks, everyone.
Thanks, Hannah. I will just share my screen at the presentation. So, as Hannah already explained, we were looking at this. I mean, this was now rather abstract than touchable. I want to go through the whole process with you, what we actually have done within our process. I have a look at the clock. I think we have some more time to talk about this. So the first step we have undertaken was looking for the proper reference. We decided to go for the BMW X540E, also referred as F15. The reason why we have chosen this one is it was the first hybrid powertrain within the core brand of BMW. And due to this fact, a lot of stuff was already published by BMW and also by other benchmarking companies like Atomic One. And we were able to simulate a whole consulting project around this without violating any IP sensitive information, and are able to talk about this in detail with you today. We focused on the starter batteries. We had a look at the technology itself, the lead batteries, the energy density, these batteries, also the case design and the idea of the standardization, modularization of the standard lead batteries today. And we decided to go for a lithium solution, lithium iron phosphate to be more precise, and just disrupt this current standardized solution, which hasn't changed for decades now. I think the first injection molded battery case with a lead chemical solution inside is like 80 years old. However, the F15 had 2 starter batteries, and we said, okay, we see there is some need to keep this a bit more modular so we can have the flexibility to adopt the capacity or power needed for a vehicle. And we wanted to have this for lightweighting reasons as well as for economical reasons within one concept, and therefore our aim was to create something modular. As soon as we came up with this, we were aware, okay, what kind, how many cells do we need? We considered, okay, what is the optimal structure to put this cell pack into a battery? How can we ensure that the assembly process will work, and what will be the optimal material to produce the case? At the bottom, you already see some other process steps which we have undertaken within the project, which will be not part of today's presentation, but we started with all the requirements and barriers which are existing right now. We generated a long list with just simple actions. We call them weight opportunities. So something, if you undertake this, you will drive down the weight, as well as complete design concepts. And we did some first drafts. We also had a look at the cost range of these concepts. We started with the electric components first because these are most expensive, and therefore we were aware, okay, we will be moving in this price range. We optimized the whole concept for an efficient and effective manufacturing process, and all the time during this process we created these one-pagers showing, okay, that is action number 1, reducing the weight by, the cost effect is X. So it becomes clear to everyone what happens to this. To give you the best understanding of the concept and to get an idea of how the battery looks like, I will just build it up with you, starting with a cell. And you see one of these cells. We took a photograph of this one. This is a lithium iron phosphate cell. Why did we go for lithium? Well, within the electrochemical voltage series, lithium is the lightest one. So we are facing a very high energy density. And there's something else interesting about this, that is that the voltage drop over the capacity is quite constant, especially if we go for lithium iron phosphate. I tried to explain this in words, but maybe it's better to have a sketch of this one. So if we imagine a diagram and we have the potential in volts, this axis, and we put the capacity, the state of charge here as a percentage, then the standard lead battery will fall pretty quick. This is quite linear, and the lithium iron phosphate stays longer on this plateau and then begins to sink. The thing is, at some point we need 12 volt. Current botnets are working with 12 volts. So this is what we need to power all consumers, and there are more consumers working on 8 volts. These are for security and safety functions. But the thing what we can already see here is that we can use more of the capacity by changing to lithium iron phosphate. And this is as well one of the drivers why we were able to exploit this weight opportunity. Concerning this, the type of cell we have chosen, we decided to go for a cylindric cell. You probably all know these from your private lives. There are also pouch cells, but we decided to go for cylindric cells. Big benefit is higher discharging or also charging rates, which is super beneficial if you look at power solutions like a starter battery. And then that is what the design was all about, is how can we take this cell and integrate this best into the battery case? And we came up with a solution that we take the most stiff point of the battery cell, and we take the holder there. So we don't damage the cell itself. We can transmit the force through it, and at the same time, by just holding it here, we still have the surface available for ventilations. So the battery is in touch with the air around surrounding this and can cool down, for example. We also designed some spare assembly spaces within the cell holder. We will use this for other electric components we will see later on. And the next thing was, okay, how many cells can we get into the battery? We have the cell holder, and of course we put all the cells into the cell holder, 20 pieces here. To stay within the area given by the standards for starter batteries, we decided to put them in a row. We couldn't extend it to a more deeper solution or super high solution. We said, okay, that is the dimensions given by the standard, and we managed to get the high pack density. You can also pre-mount these modules and then just slide them into the case. Benefit of having the shape of these cell holders here, which is exactly the same shape as we will see in the next slide in the case, that this will support our battery case and allows us to use a thinner wall thickness of the case. We see here the case, same prismatic shape as the cell holders, increasing also the stiffness of the total battery case, brings us some benefits regarding crash. And it also covers our electric components within the battery from, let's say, water. And that, what you see now in the upper left picture, is the first time we talk about a module of our battery concept, which leads to an interesting part. Either one module is enough, then we can just simply put a cap on this one and mount it in the car. Or what was the case with the reference car, the F15, was we needed more modules. So we said, okay, we need a connector instead of a cap. Thing here again, if we have two modules, the battery mounting will be in the middle. So we can use the connector as well as to transmit the forces through the battery, still keeping the cells safe. And we use therefore this yellow ring you can see here. The same is also beneficial for manufacturing processes because it allows us a shorter cooling time and leading to less warping. We designed the connector as well as the caps for version G. This one is called with a snap fit, enabling us to reopen the battery case without destroying something. And we have these cutouts through the whole, as well as through the connector, as well as through the case. And we can use this for the robots for automatic assembly within the serial production. For the F15, I already mentioned it, we needed more capacity and more power. So we added more cells still in the same row. We added a second module to it. We used the spare parts at the top. Top is beneficial in terms of that the battery management system will get hot through usage, but the heat is not going through the cells because it's rising up, and then we can again save our cells. We still have enough spare space on the left side. Now you see here these thin green lines here. Maybe I'll make a small arrow there, this one. So the battery management system has the same size as these two battery packs. So we still have the space free on the other side. We can use this for additional systems. For example, if needed, an additional cooling. If it's not needed, we can move the battery management system to the middle, improving, for example, the center of gravity. To complete the whole battery, we just closed the case. We have the mounting at the top, at the bottom here. That is what is required by standards. We have the terminals at the front where we can put the cables on. We have some holes on top for the valves. In case of an emergency, battery cells exhaust gases. Then we can take them from there through the valves. Regarding the material, we decided to go for polypropylene and partially use recycled polypropylene. Has some environmental friendly thoughts within. To sum up what then happens, the value of a pound, or sorry, being the German guy, I'm looking at euro per kilograms. We had two steps. First step was, okay, we take the whole concept. We know, okay, how much material is needed, what kind of tooling does this require, what is the cost for assembly processes. We need to buy cells and battery management systems, or this is cost for us. There will be other manufacturing related costs, let's say rent or air supply needed for the machine, all this kind of stuff. And that was our manufacturing cost. We put some surcharges on top of this to make sure that we also cover other costs like the pure engineering, the overhead costs, and of course the margin, because the pure manufacturing cost will not be the cost of the OEM buying the system or a system like this. All this led through to the chart shown on the right side. You see the total cost. Y-axis, x-axis is the production volume per year. And the marked one is version G, the one with the snap fits we have seen on the pictures on the slides before. We start with 23 euros per kilogram, go all the way down to 16 euros per kilogram, mainly driven by the cell costs, of course. And maybe one more note to this, that is just the cost we could directly address with the concept. Of course, there's more costs related to this. For example, we'll see on the next slide on the summary, the battery case will be smaller, the whole battery is smaller. We save approximately something like 10 liters. So we could move the battery a bit more to the front of the car. By moving it to the front of the car, we need less cable because the engine is still in the front of the car. We need, for example, 1 meter less cable. We save as well the kilograms for this 1 meter of cable, as well as the cost for this 1 meter of cable. That would be, for example, one effect which drives down the light weighting cost in the second step, if we consider secondary effects. Summing up the whole thing, we were able to create this modular concept, saving more than 33 kg. It's probably more something like 33.5 kilograms. We saved these 10 liters, we tripled the life expectancy. And we did so by consolidating both lead batteries into our modular concept. We substituted the lead by lithium iron phosphate. We used the cylindric cells to exploit the better capability and also the safety properties of these cells available on the market to enable us to use these higher discharging currents. We minimized envelope space and other stuff, the envelope space as well as the lever arms, all this leading to an optimized design. We also had some twerks on the manufacturing issues to make sure that the efficiency is given. And we are now at a point when we look at the concept that we see more benefits concerning how to integrate this battery concept within the vehicle. We think it might be beneficial not to put it where the battery is right now with a standard battery holder, but to integrate it better. And then we could also save more weight. Regarding these small written notes at the bottom, I think there's two factors worth mentioning now. The first one is I want to start with is the whole concept also works at the 48 voltage application. So we could still use this even if it's not 12 volts anymore in our current board net, but 48 volts. And to give you a better understanding, that's my second point, of the capacity. You have just seen some green cells on the screen. One module will be enough to cover a small car and also a battery electric car. For example, a Tesla Model X is still using a starter battery, and one module will be enough to power this one. When we go for two modules, we are looking for cars with a higher performance need, probably more power, like the F15, but also V12 motors like we know them from the Lamborghini or Ferrari. The carbon look you see on this picture is just some aesthetic thing we added afterwards. I give you a super brief outlook on the net zero effects. We already had this in the beginning of the presentation. The vehicle weight is related to carbon dioxide emissions. So the lower the weight is, the less carbon dioxide is probably emitted. And when we reduce the weight of the starter battery, in this example by 33.5 kilograms, we will be able to also to reduce the weight of other parts like the battery holder. When the battery weighs instead of approximately 41 kg, it just weighs a bit more than 7 kg. We can for sure make the holder a bit smaller, can make it a bit more thinner, saving more weight. The same happens probably to the wall where the battery holder is mounted to. And by reducing the package, the 10 liters, these 10 liters are now free for other actions. And all this leads to the third point here, that we support the electrification of vehicles by driving down the weight and decreasing the package needed. You have seen already that we have a smaller battery case now, needing less material because it's just less volume. And because it's less volume, of course, and less material, we also need less energy to heat up the whole thing. And this reduces the carbon dioxide emissions also during the production. Lithium iron phosphate. We expect this to last 3 times longer than the standard lead battery. I don't know, probably you change your battery right now 4 to 5 years. We expect this with the lithium iron phosphate to be in the area of 13 years. And last but not least, our snap fits enable easy repair and recycling processes. You will be able to just open the battery set, you might change the cells, you might repair something, then you can close it and you can still use it. And this being said, I'm through my part of the presentation and hand over to Steph for the closing questions. Thank you very much.
Thank you very much, Florian. Yeah, so we will open the question forum. We had a couple come in just during your presentation there, Florian, so I'll just jump right into a name I recognise. Professor Prashant has asked, do you use this particular type of battery for both cathode and anode, and can the pouch give a constant voltage?
Can you repeat the question, and maybe I can read it also?
In the chat box, so you see the chat box?
So the first question, I mean, the question is, are we talking about charging or discharging? But if we talk about both processes, yes, cathode and anode will change. So yes, for both.
Okay.
And the second one, yes, pouch cells, as soon as we use the lithium iron phosphate, give you the same diagram. That was not the point why I was sketching this. That was for lithium iron phosphate, not for cylindric cells versus pouch cells.
Thank you. Another question from Professor Prashant. How is cooling air circulated through the battery pack?
Okay, maybe we go back to
and it's with specific reference to the batteries in the interior of the pack.
So the question is about how the air is circulating within the battery?
Yeah.
Okay, we have the valves on top here, and we still have some spare space here, which is not shown, but we can also think about this thing here. Just imagine that the battery management system is on the other side. So we could have the cooling device here. We still have the spare parts here, as well as these, what should I call this? These parts here, they are also hollow. And there's still some distance between the cell. That is the idea of the ventilation concept, to keep it simple. Does it answer your question?
Professor Prashant, if you could type yes or no into the chat box, that would be really helpful to know if that's answered your question. Another query that we've had, could you consider, and this is probably Graham and Florian, multi-materials? What would be the approach to developing a cost model for a multi-materials part? You know, if 2 types of materials are bonded together.
I'll make my answer quite short and then hand over to Grimmy. I say yes, we can do it for both, and it probably makes sense to go for different materials.
Yeah, so with respects to how the cost modelling software works and how the approach works, really what you do is a sort of kind of modular approach. And by that I mean, when you develop the model, you build in the portions of the model are reflective of the material and the process for that material. You then build steps into that model, which would mimic whatever drawing processes you would need. So if you're welding, you're gluing, whatever your process may be, and then also you can associate costs with that. So using this kind of modular approach gives you like a top level cost, which you can then break down into isolating, I guess, the costs across all those modules. And that can be really powerful because that gives you the opportunity to really go in and assess the design and you can identify the points that are, oh, that's a pinch point for us in terms of cost, or there's a process time consideration there, because the model also takes things like process time, etc., into consideration. So it can provide quite a robust output. And so yes, to answer Florin's questions, it is possible. Sorry, response as well, it is possible, and there's a bunch of different ways to do that.
Thank you very much. Another questions came in via the chat box there. So in terms of the mass production of this particular battery and implementation or field trials, how close are we to implementing such a concept on a greater scale?
Yeah, I love this question. It's a good question. We're at the moment in a few negotiations, bring this concept down the road and bring this also in the cars. But that's all I want to say right now to this. We can get in touch later if you have more ideas, maybe some synergies we can use for cooperation. I don't know what your background is. We are open to discuss it with you. And yes, there are ideas and we are working on this.
Thank you very much. Yeah, you can, for all the attendees today, you can actually see a couple of email addresses there. So feel free to take a note or take a picture of this particular slide. And for the NMIS inquiries, if you could contact Hannah. And for any information, or you get more information on TGM, Florian's email is there as well. This is a patented TGM product, so if you have any queries about this particular starter battery, then please direct them towards Florian himself. There's also, for general questions, there is also the NMIS inquiries email address, which has been popped into the chat box for anyone who has a general query about NMIS. Another question from Professor Prashant. Are you thinking of lightweight IC engines?
Why not? We had this in the beginning. There will be some function or some requirement, what the customer needs, or what the market wants to see in a car, which might be fulfilled best by the IC solutions. And for sure, there are still potentials we can find on the ICE ones. So yes, we definitely believe that an ICE engine can be lighter than the one we see right now. And there's also a lot of stuff happening within the last years. So yes, that is something we were also working on.
From an NMIS perspective as well, we are looking a lot now at topology optimization. So different softwares that offer that capability and different manufacturing processes that best support that, especially particularly within the kind of additive manufacturing environment where, you know, there's more novel approaches and more novel geometries that you can potentially achieve. So really, you know, from a MER perspective, it's collaborating with partners that are looking to undertake that type of investigation study and potentially support them in the future.
Thank you. Another question came in from Jonathan Corney. Do supercapacitors have any potential advantages for starter batteries?
I like the question. So the patent also leaves open what kind of energy source we use. So if we, for example, take a supercap, this would work for the same concept as well. I like the idea because the power density is higher for supercaps. There's only one big disadvantage, which is that they are pricier than these lithium iron phosphate cells, so our lightweighting cost will be higher. But yes, I also do know some cars using supercaps right now. Sometimes that is also the solution, and if we find this is the prices for supercaps decline faster than for the cells, maybe this is the best solution. I mean, they provide the highest power density or higher power density than the standard battery cells.
Thank you very much. Any other queries or questions to come in just now? Absolutely, Prashant. If you get in touch with Hannah initially, yeah, we can see what we can do. Thank you. Prashant, you've said lightweighting of IC engines. Instead of this particular battery, the actual engine itself. Something you would like to tackle? Lightweighting a full engine?
Steph, I don't know whether you broke up a bit there. Would you mind repeating that question? Thanks.
Sorry, can you hear me okay now?
Yes.
Yeah, okay. Prashant has actually asked it's actually the lightweighting of the IC engine itself. Is that something that you would tackle, Florian and Graham?
Sure, we would be down for a project like this.
What are the complexities that you would see in something like that?
Sorry, Steph, I couldn't hear you properly right now.
Sorry, I would say what would be the complexities in tackling something like that?
To get all the requirements clear in the beginning, I think.
Absolutely. Yes, Prashant, please feel free to send on some of the papers on the work that you've done. That would be great. There are, as far as I can see, there's no more questions in the Q&A, and nothing came in on the chat tool. Does anyone else have anything they would like to bring up today with the guys? I'll just give a couple of seconds for typing. I think that's all the questions, Debbie.
Okay, thanks very much, Steph. Just like to thank all our speakers, Hannah, Steph, Graham, and also a special thanks to Florian from TGM for joining us for today's NMIS Insights. As Steph has previously mentioned, you will receive a survey just after this webinar, and we'd be really grateful if you could take a few moments to complete this. Your feedback does help us shape future NMIS Insight webinars. There is one next week on Wednesday, the 5th of May, that will explore what's happening at our Lightweight Manufacturing Centre. If that's of interest to you, you'll find details on our website at nmis.scot. I'd just like to thank you all very much for joining us today, and we'll now just bring this webinar to a close. Thank you.
Bye.
Yep, thanks everyone.
Take care, everyone. Thank you very much.